Hello, I'm Seema and welcome to part 4 of the chapter Chemical Bonding and Molecular Structure. In the previous parts, I described the Causal-Lewis approach to chemical bonding to you. Then I explained the Langmuir-Lewis approach, and after that I discussed the octet rule, where I told you that all atoms in all compounds are in a race and they are trying to acquire 8 electrons in their outermost shell. And this number, this magical number of 8 is known as the magical octet. It is known as the octet that all atoms try to achieve, and it is because of this octet that they participate in chemical bonding. After that, we discussed the Lewis representation of atoms and molecules, and I showed you how to draw the Lewis structures. And finally, in the previous video, I told you about formal charge, how we assign charges to each and every atom in a molecule, and that structure, that Lewis structure which has the lowest formal charges, is chosen to be the final Lewis structure for us. Now I will discuss the drawbacks of the octet rule, or let us say the exceptions to the octet rule. We did say that all atoms are always in this constant race to try and acquire those 8 electrons. But we find that this is not a strict rule and it's not followed always. There are exceptions to this rule. So what are these exceptions? We'll just notice a few of them, and usually as a question you may get, what are the drawbacks of the octet rule? You cannot really call it the drawback as such, but these are the limitations of the octet rule. So we call them the limitations of the octet rule. Where is it that we cannot apply the octet rule? The first condition that we see in certain compounds is that there is an incomplete octet. The octet itself is not complete in such compounds. Take a look at lithium chloride. Lithium chloride is LiCl. Lithium has 1 electron in its outermost shell, and it combines with chlorine, which has 7 electrons in its outermost shell. And when it forms a compound with chlorine, lithium chloride is formed, which has a formula of LiCl. Now, in this compound, chlorine completes its octet, but lithium only has 2 electrons in its outermost shell. As I explained to you, that those elements which only have the first shell has a maximum capacity of only 2 electrons. So hydrogen and helium would always have, helium does not combine because it already has its outermost shell complete. The outermost and the first shell has a maximum capacity of 2 electrons, so helium has completed its duplet, we call it, since it has a capacity of only 2 electrons. But hydrogen can share, or it can gain an electron to get its duplet. But all other elements from lithium onwards, they have electrons in the second and the consecutive shells. So lithium is present, the outermost electron is present in the second shell. It has only 1 electron in its outermost shell, which is the second shell. So it should expand to form an octet. But I also told you in a previous class that gaining or losing 1 electron is easy. Gaining or losing 2 electrons is difficult. Gaining or losing 3 electrons is very, very difficult. And gaining or losing 4 electrons is impossible. So, because every little change that is brought about in an atom requires energy. And the amount of energy goes on increasing as the amount of change that you are trying to bring about increases. So if you try to add 7 electrons to lithium, if adding 4 electrons is impossible, adding 7 electrons is totally out of question. So lithium, we find instead of forming an octet, it only stops at a duplet. So we find that lithium, it only stops at forming a duplet, that 2 electrons in its outermost shell, yet it forms that kind of a compound, because even that, the 1s orbital, when that completes, even that gives it some amount of stability, right? Similarly, beryllium has 2 electrons in its outermost shell, and in order to acquire the octet, it might either have to gain 6 electrons, impossible, or It can lose 2 electrons. Again, the size is so small and the electrons are so close to the nucleus that it's not easy to lose those electrons either because of the charge, the attraction being felt by the nucleus. So beryllium, it forms covalent bonds. It shares electrons, and we find it shares electrons with 2 hydrogens and it forms a dihydride. And this is again, how many electrons does beryllium have? It has 4 electrons in its outermost shell instead of having the octet. Boron also, we find, has 3 electrons in its outermost shell. Combines with 3 chlorine atoms, the octet of chlorines is completed because each chlorine forms a single bond with the 3 electrons of boron, and the octet of chlorines is completed, but boron in the end after bonding has only 6 electrons. So we do find that in certain compounds, the central atom may not achieve the octet. And we usually find such compounds of elements which have 1, 2 or 3 electrons in their outermost shell. These are the ones which usually show an incomplete octet. They do not show compounds where they have a complete octet. Then, so this is one exception to the octet rule. The second type of exception that we notice is that we always talk of lone pairs of electrons, bond pairs of electrons. We are used to talking of electrons in terms of pairs. But in the case of certain molecules, we find that the electrons may not be paired. You may have odd electrons after all. So such molecules are known as odd electron molecules. For example, nitrogen combines with oxygen to form NO, and in this, nitrogen forms 2 bonds with oxygen. So octet, which has oxygen which had 6 electrons in its outermost shell, completes its octet. That is, it has 8 electrons after bonding, but nitrogen, which had 5 electrons in its outermost shell, used 2 of its electrons in the covalent bonding with oxygen and has 1 lone pair and a single electron that is also left behind without bonding. So, such a molecule does exist, but it's an odd electron molecule. So, the nitrogen, usually elements which have 5 electrons in the outermost shell, may show such compounds. 5 or 3 may also show such compounds. So nitrogen here forms NO2 also, and in NO2, this compound also, we find that nitrogen has the odd electron. Oxygen forms 2 bonds here, the octet is completed. The oxygen here has 6 electrons and 2 of these electrons are from nitrogen. One of the pair of electrons from nitrogen is participating in a coordinate bond. And let me remind you, a coordinate bond is a bond in which it is a kind of a covalent bond for all practical purposes. The only difference is that both the electrons are contributed by 1 atom in a coordinate bond. Not usually in a covalent bond we believe that both atoms contribute 1 electron each. So, if it has a coordinate bond, nitrogen acquires a partial positive charge and this oxygen has a negative charge. But NO2 does exist, and again the nitrogen here has a single electron, so this is also an odd electron molecule. Now in the previous class I told you about H2SO4, and there was one specific point that I deliberately avoided because I knew that I'll be explaining it now. The next type of compounds that you have are the expanded octet. Let me again remind you about something that I taught earlier. When we did the periodic classification of elements and we were doing the valencies of the different groups, we said for representative elements, the valencies are either the name of the group, that is the number of the group, the number of valence electrons, or it is 8 minus that number. So for elements having 1, 2, 3 or 4 electrons, the valencies are 1, 2, 3 and 4. But for elements which have 5, 6 or 7 electrons in their outermost shell, they can show valencies of either 5 or 3, 6 or 2, 7 and 1. And on the other hand, I also told you that elements gaining or losing 1 electron is easy, 2 is difficult, 3 is very, very difficult, 4 is impossible. But sharing of electrons is not impossible. So such elements which have 5, 6, 7 electrons in their outermost shell, they tend to expand their octet too. They tend to go beyond the 8 electrons. And why do they tend to go beyond the 8 electrons? If you look at the electronic configuration, let us say for phosphorus. Phosphorus has 5 electrons in its outermost shell. So it has the 5 electrons in the outermost shell means that they would be 2 electrons in the s orbital and 3 electrons in the p orbitals. But you still have 3 electrons in the p orbitals, there are 3 p orbitals. And you have 5 d orbitals also in the same shell. So when you have 5 d orbitals, in the case of phosphorus, phosphorus is the 15th element. Hydrogen, yeah. Phosphorus is the 15th element, so let's write the configuration of phosphorus. Phosphorus would be 1s2, 2s2, 2p6 makes it 10, 3s2 and 3p3. So in addition, after 3p, we know it is 4s which fills up, but 3d orbitals are available to the atom. So such an atom can expand its octet beyond the 8, the number 8. And some of the electrons can go into the d orbitals and then participate in bonding. So such compounds do show an expanded octet. Although the next after 8 electrons, that is the 6 electrons in the p orbitals and 2 electrons in the s orbitals, the 9th electron should go to the next shell. But since there is an availability of orbitals in the same shell, such atoms may push electrons into those orbitals and those electrons may participate in bonding, leading to an expanded octet. So such molecules are said to have the expanded octet and they do not follow the octet rule. So phosphorus in PF5, phosphorus pentoxide, which has 2 electrons in the 3s orbital and 3 electrons in the 3p orbital, one of the electrons of the 3s orbitals jumps to the 3d orbital and now there are 5 electrons available for covalent bonding. And all the 5 electrons, they participate in covalent bonding with 5 fluorine atoms. And fluorine has 7 electrons in its outermost shell, being a halogen. So every fluorine forms a single bond with phosphorus, and with the sharing of one pair of electron, every fluorine has 7 plus 1, 8 electrons, their octets are completed. But phosphorus, if you look at it, it has 5 covalent bonds around it, which means how many electrons does it have around it now? 5 of its own and 5 that it has bonded with. So it is a 10 electron system. It's a compound which has the expanded octet for the central atom. Similarly, if you take a look at sulfur now, sulfur has electronic configuration. After phosphorus, it's the 16th element, so this would be 3s2, 3p4. So there are 4. These 2 electrons, one from the s orbital and one from the p orbital, which are paired. Okay, let me just explain this to you. I'm making the outermost shell. In the case of nitrogen, there was 3s and 3p had 3 electrons. And it should have been here, but since I do not have space, I'm making the 5d orbitals here. 1, 2, 3, 4, 5. So in the case of phosphorus, what happened? One of these electrons jumped from the 3s, 3p, and this is 3d. One of these electrons jumped from here to 3d, and thus there were 5 unpaired electrons which participated in the bonding. In the case of sulfur, we have 2 electrons here and 1 electron paired here. So 1 electron from the 3s and 1 electron from the 3p jumps to the 3d, and now we have 1, 2, 3, 4, 5, 6 unpaired electrons. And these 6 unpaired electrons, they would form bonds with the 6 atoms of fluorine. So we have sulfur hexafluoride. And if each fluorine has 7 electrons, it requires only 1 covalent bond to complete its octet. So every fluorine is completing its octet by forming a single bond with sulfur. But sulfur is using all of its 6 electrons in covalent bonding. Therefore, sulfur has an expanded octet of how many? 6 into 2 would be 12 electrons. So this would be a 12 electron system. So in SF6, sulfur has an expanded octet. The octet rule is not followed here again, right? So another compound that I did in the previous video was H2SO4, where I explained the formal charge and I told you why the formal charge, when both the oxygens have a formal charge of 0 and sulfur also does, that is when we choose this to be the final Lewis structure. Now, we notice that when we have this as the final Lewis structure, there is a problem. And what is the problem? Although oxygen, hydrogen, all the oxygens and hydrogens have their octet and duplet completed, sulfur here goes beyond the octet. And that is the reason why we accept it beyond the octet, because again, in sulfur, one electron from the 3s jumped up to 3d and one electron from 3p jumped up to 3d, making 6 electrons available for covalent bonding. And all the 6 electrons, they bonded to form these 6 bonds around sulfur. So in H2SO4 also, the sulfur is a 12 electron system. This molecule is a 12 electron system. It has, sulfur here has the expanded octet. So we find that the octet rule is not a strict rule that is always followed. We do generally find molecules trying to acquire that octet. That is a number that definitely most atoms and most compounds try to acquire. But it's not a strict rule because it's all a game of energy. If by using a little energy, the electron can be pushed to another shell and it leads to a greater stable structure, why not? So we find such exceptions to the octet rule. It does not mean that sulfur does not form compounds where it has the octet completed. For example, SCl2, in SCl2, sulfur forms 2 bonds with the 2 chlorines around it. And the 2 unpaired electrons that sulfur had initially were in the 2p orbitals. Here, this was paired and this was paired. It actually had only 2 electrons available for bonding. So it forms compounds where it has only 2 electrons and it forms only 2 bonds. But it can show compounds where it has an expanded octet too. Now, expanded octet is not possible in the case of elements which are present in the second period. The reason being that in the second period, the electrons, the valence electrons are in the second shell. In the second shell, d orbitals are not present. The d orbitals are not, 2d orbitals are not there. They do not exist. D orbitals exist only in the case of from the third period onwards. That is the third shell onwards. So the second period elements do not show expanded octets, while the third period onwards, those elements could show the expanded octet. So this has to be kept in mind. It can come as a question, why do second period elements do not have expanded octet molecules? Now, what are the other things where you find that octet rule does not apply? If it was true that all elements try to acquire 8 electrons in the outermost shell, we already know about the duplet, that in the first period, they have only 1 shell. There's no chance of an octet because they have only 2 electrons. That is acceptable. Their capacity is only of 2, so obviously they can't make an octet. But if all elements are trying to acquire 8 electrons and these 8 electrons is the configuration of noble gases, then noble gases should never ever react under any conditions. They should never react. But we find that noble gases, although they usually do not react, they are found in the gaseous state, they do not even form molecules usually, but they are shown to form certain compounds. Some of the noble gases do form compounds, for example, xenon difluoride, krypton difluoride, xenon oxyfluoride. These are compounds which are known to exist. So if noble gases themselves are forming compounds, then octet rule cannot be the final rule. There are major exceptions to the octet rule. But yet, we cannot ignore this rule because majorly, about let us say 95% of times, the octet rule is followed. So it is very, very important, but it does have exceptions of this kind. So if noble gases is the aim of every element to achieve that configuration, then noble gases should never react. But they do find to react. We do find them to react. Then, these are just excuses to find faults in the octet rule, believe me. It says that the octet rule does not explain the shapes of molecules. That was not the aim of the octet rule. The octet rule only tells us that this is a certain number that they are trying to achieve. So, the limitation, you can say, it only tells us about that. It does not tell us more. So it is limited in that way that it does not tell us about the shapes of molecules. It does not tell us why about the relative stability of different molecules. This is one molecule, this is the other one. This one is more stable, this is less stable. Why is it more stable? Why is it less stable? How is energy associated with that stability? How do you relate energy to stability? So these are things that the octet rule does not tell. Now, these are topics that should be covered by other rules and other studies, but yet these are just faults, finding faults, with the rule. I somehow feel it's just deliberately trying to find faults in that rule. But these are definite exceptions that you must learn about. That you have the incomplete octet, you have compounds which have odd electron molecules, you have compounds which have the expanded octet, in which atoms have an expanded octet, and noble gases which were not supposed to react because of the octet rule. We find them also to be reacting, so the octet rule cannot be the final word. It has a lot of exceptions. And when you're attempting a question in the paper, if you may get points for this, you can definitely add these points saying that they do not explain the shapes of molecules, they do not take into consideration the energies of molecules, and hence cannot compare the stability of the molecules based on their energy. So these were the limitations of the octet rule. If you found the video helpful, please give it a thumbs up, subscribe to my channel, recommend it to all your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye.